Okay, so we've got a new topic for today. We're going to talk about complex inner product spaces. It's highly analogous to things that we've been doing already, but importantly different. So the first thing I want to do is I'm going to start with a confession, a mea culpa. And the point of that mea culpa is going to lead us into the sort of the new idea for today. Okay, so long time ago we defined something called vector spaces. Well, that's what we sort of casually call them. That's how we sort of, conveniently casually thought of them. Specifically, what we defined was something called vector spaces over the real numbers. So specifically, scalar multiplication was in the definition as only by real numbers. And let me just take you back to that page. This goes way back in our notes to, early chapter 2, section 2.1, right? And notice right here, vector space over the reals. And it says right here, scalar multiplication by real scalars. Critically, real scalars. Okay, now that's not something that we dwelled on. In fact, I kind of glossed over it. In fact, I glossed over it on purpose. And the reason I glossed over it on purpose is because I wanted to be able to bend that rule in certain cases. So here's one of them. Here in chapter 4, we were looking at solutions to differential equations, and we say, okay, well, characteristic polynomial, find the roots, and then we ask, what happens if you have a complex root? Well, you get a complex valued solution, which, right off the bat we weren't afraid of. But we decided, well, maybe we should get sort of real versions of that. And then look what we did. We took a linear combination of two functions using coefficients, one of which is complex. Right, so we broke our rule. Right? We were talking about the vector space of solutions to these kinds of differential equations. Vector space, well, of course, the only sense in which to define vector space was vector spaces over the reals. It says right here, you can only multiply by real scalars. And what did we go and do? Well, we multiplied by a complex scalar. That is a little math crime right there. Right? So now again, I did that on purpose. This is what I like to call a victimless crime, in the sense that there's a way to fix this. There's an appropriately analogous definition that you can make. Everything goes through just fine. But in order to fix it, in order to treat this properly, it would have been quite a distraction. A lot of other things to think about. And recall, we had a lot going on at the time. Solving differential equations, thinking about vector spaces and dimensions and linearity and lots of various different kinds of cases. There's a tremendous amount of stuff going on. We didn't need the other distraction. This is just a formality away from a perfectly valid argument. And again, at the time, I didn't think it was worth making a fuss about. Okay. Because it comes through the same way if you do it right. So now, analogously, here's another situation in which we kind of cheated, sort of a little bit. Eigenvectors we talked about. Well, sometimes with a matrix, you might have complex eigenvalues, and for that complex eigenvalue, you might get correspondingly a complex eigenvector. That's just kind of, writing it down, going through playing the game. But notice when you write it down as AV equals lambda V, notice this scalar is complex. Again, kind of breaks our rule. Okay, another victimless crime, another nothing to worry about. This does not, this is just a kind of a formality. So, nevertheless, I do want to confess we did break some rules here. Now, if you may ask the question, well, if it doesn't matter, why is it a rule? Why do we specifically say only real scalars? And the answer is because while in these cases it didn't matter, in some cases it does. And I'm going to show you a very quick and I think very persuasive instance of when it matters. And that is, let's think about the complex plane Let's think about the complex plane, and let's think about it as a vector space, and let's ask what is the dimension of the complex plane. Now you may think, okay, come on, that's preposterous. What is it? Ridiculous exercise. It's a plane. Of course it's two-dimensional. That's what planes are, for crying out loud, right? But look what happens. If you allow complex scalars, then the complex plane is in fact one-dimensional. Don't think about your geometric intuition for dimension. Think about what is a basis for the complex plane, right? And let me color code a little bit better here. If I want to talk about vectors in the complex plane, I claim that a basis consists of just the number 1. I claim that you can think then of every vector in the complex plane as being a scalar multiple of 1, the complex number 1. How do I know that you can do that? Well, I can tell you exactly what that complex scalar is. That complex scalar is, Z. Right? And so, this is a basis. The number 1 by itself is a basis for the complex plane if you allow complex scalars. This is very unsettling, right? Planes are supposed to be one-dimensional. Something has gone terribly inconsistent with our intuition. As a result, explicitly, directly as a result of our allowing complex scalars. Now, if you don't allow complex scalars, if you stick to the rules, as it were, and require using only real scalars, if you require real scalars, then, you need 2 vectors to form a basis, and not hard to persuade yourself that every complex number, Z, if you want to write it as a linear combination of these basis vectors, 1 and I, right, then those scalars are the real part A and the imaginary part B. Right, so you require real scalars, and all of a sudden we're back to the complex plane being two-dimensional, as of course it should be because it's a plane. Right, okay, so the point here is to realize how important the subtlety of what do we require of our scalars, how important that is in some cases, such as this one. Right, it really, really dramatically fiddles with our notion of dimension. On the other hand, in terms of manipulating solutions to differential equations, that's not a big deal. It's nothing to worry about. Okay. Here's an exercise for you all to work out on your own. Cn. This is something we're going to study quite a bit today, anyway. Cn, it's just like Rn. Just instead of having all real coordinates, it now is allowed to have complex coordinates. And if you allow complex scalars, I claim that the dimension is n, whereas on the other hand, if you were to allow only real scalars, the dimension would be 2n. And in each of those cases, I think it'd be a nice exercise to try to write down what's a basis for each of those senses. Right. By the way, it's going to be kind of a mashup of the bases that we just used for the complex plane itself, and the standard basis for Rn. Just kind of combine the 2 different ideas and those 2 different bases, and those will answer these questions here. Okay. All right. Good exercise. So moving along, Cn then has to be treated carefully. We can't just walk around in Cn and pretend like everything's just the same as it was in Rn. Going forward, it's going to make a difference. Things are going to matter. Okay, so here is where we're going with this. Reminder, with this idea of a vector space, we built up on top of that idea of a vector space a more sophisticated structure called an inner product space. And the idea of an inner product space was based on the idea of the dot product. Very importantly, though, the real dot product in Rn. So, if we are now in Cn, hopefully I've persuaded you that Cn is a very, very different place, right? Things that seem to be not important are actually really important. And so we can't just say, oh, well, Cn, let's just tack on an inner product, kind of like we did in Math 212. What's the difference, right? That's dangerously naive. We can't just do that. We have to worry about, given this new complex structure over which we're trying to define vector spaces, complex scalars, everything being different, can we define something kind of like a dot product? And this is not immediately obvious. Disturbingly, this is going to sound weird to say, the dot product itself actually doesn't behave very much like the dot product. And I say that deliberately, awkwardly. What I mean by the dot product in this context, now it was not intended. This formula right here was never intended to be done in Cn, right? In Cn, it does not behave like it did in Rn. It importantly fails some important conditions. So here's the big one, really. You remember we have, on our list of requirements for an inner product, a self inner product should only be 0 if the vector is the 0 vector. Well, look at that vector. Self dot product, 0. That's extremely weird, right? This is not how dot products are supposed to behave. Nothing vaguely resembling this ever happens in Rn. You can't have a non-zero vector whose self dot product is 0. It's just highly inconsistent with the ideas that we had in Rn. So we are in a bit of a bind. We would like to do something kind of like dot products. We're in this new context, though, where everything's a little bit different. And we can't use our old dot product because it crashes, burns horribly. So what do we do? So you could hope to find a different formula that in Cn behaves identically with exactly the same 4 properties, exactly the same as the good old plain old dot product in Rn. That would be a nice goal. But there is no such thing. So we have to relax our goal a little bit. What we're going to try to do is, instead of trying to find something that behaves exactly like the Euclidean dot product, we're going to try to find something that looks kind of like the Euclidean dot product and that satisfies properties that are close enough, kind of like the dot product in Rn. And there is such a thing. It is called the Hermitian dot product. This is just an algebraic choice, right? We define this thing called the Hermitian dot product on Cn. So keep in mind, when we say on Cn, what we mean is that these vectors to which we apply this new construction, this new formula called the Hermitian dot product, those vectors are vectors in Cn. They're in tuples of numbers, but those can be complex coordinates. Right? And the formula, very straightforward. It's a sum of products. Kind of looks a lot like the good old, plain old dot product. Key difference, this is weird, but you conjugate the coordinates of the second vector. That's what makes this a Hermitian dot product, with the little subscript of H there, representing it being a Hermitian dot product. Conjugate the coordinates of the second vector before you multiply and then add. I mean, it's a choice, making this up. By the way, don't forget we have this alternative formulation for how to write dot products. Remember, we just did this last time, but dot products we sort of interpreted as transposed matrix products. So along those same lines, notice that we can view this Hermitian dot product as a transposed matrix product with a conjugate, again on the second vector. Okay, so now this is a choice. I'm making this up. Why are we making this up? And is this a good thing? Well, this is a very good thing. As it turns out, it has properties. This Hermitian dot product has 4 properties that you will notice are really, really close. Not quite, but really, really close to the 4 properties of the dot product on which we modeled our general inner product construction. So you'll notice the symmetry property and the sort of right distributivity property and the pulling out scalars property, and then the sort of the self inner products not being 0 property. Right. So those are all familiar. The subtle differences you will notice because of the fact that these are Hermitian dot products and thus conjugate on the second vector. It's not exactly symmetric. It's conjugate symmetric, you might call it. Okay. When you pull out a scalar from the right side, well, keep in mind that scalar was on the right side. It was going to get conjugated. So when you pull it out, it's still got to get conjugated. Right, so pulling out a scalar from the right side, just the right side now. When you pull out a scalar from the right side, it doesn't just pull out, you have to add conjugate. Other than that, the properties are the same. So this is really close, and this is as good as we're going to get. If you say, I insist that we find a formula that has exactly the 4 properties of the dot product in Rn, too bad. There is no such thing. Okay, so now this is a little unsatisfying, right? We have a lot of familiarity with the dot product from Math 212. Got used to it as viewing it as being something that's natural, geometrically natural. We've seen physics applications of it, and that's not, it seems like that's what a dot product is supposed to be, and we're just making stuff up here. Right? And I get it, right? I mean, I kind of sympathize with that. But 2 observations I want to make. First of all, despite that, there was a time that was your first time seeing a Euclidean dot product, right? And at that time, it might have seemed like, hey, aren't you kind of making stuff up? And then, well, it was an algebraic construction, and you go through and compute, and then you find that it has certain nice geometric properties, and it has certain nice applications to physics, right? So we're actually in a kind of analogous situation here. I have a new construction, and yeah, you haven't seen it before, and yeah, it seems weird, right? But we're going to find that this construction, however strange, does have some really nice applications. Okay. Mostly coming out of the fact that as an algebraic operation, it has nice properties, right? This is the big key. Okay. So don't stick with this monster just because it looks familiar. That monster has terrible algebra, right, in CN. Familiarity is not as important as good properties. Okay, here's the second observation I'd like to make. This formula here, seemingly brand new formula, this Hermitian dot product. You say you've never seen this before. Here's the thing, though. Think about what happens when you apply this Hermitian dot product to real vectors. If you apply this product in Rn, this process here of conjugating, if W is already a vector in Rn, the conjugation doesn't do anything. This is our old friend from Math 212 when you apply it in Rn. Right? So, case could be made that, when we wrote down the formula in the first place in Math 212, when we wrote down that formula, we wrote it down the way we did because we weren't thinking about, hey, how should this most naturally generalize in a complex setting? You could make the case that we just wrote it down wrong in Math 212 in the first place. This is really the more natural way to write it down. This is exactly the same operation as the Math 212 dot product in Rn. So it's not really new. It's just a new way to write it down. And arguably this is, like I say, a more natural generalization for the complex setting than our previous naive notation would have suggested. Okay, so enough of that. Here's our definition. I guess I have to say another couple of quick things. There are variations of this. So notice what we've defined here is specifically the Hermitian dot product, right? When we were doing real stuff, we generalized the notion of a dot product to a more general construction called an inner product. Right? You can do the same thing here. We're not going to spend any time on this in Math 216, but just so you know, any function that behaves the same way we call a Hermitian inner product. Furthermore, you don't have to restrict your attention to Cn. You can consider other vector spaces with complex scalars. And you can talk about Hermitian inner products on those complex vector spaces. This is, in fact, what you do in quantum mechanics. If any of y'all are planning to take a quantum class, or if there's any intro quantum in engineering, I don't know if that's the case. But quantum mechanics, a certain aspect of quantum mechanics, takes place in a vector space with complex scalars. Wave functions of particles, as it turns out, are vectors in a complex vector space. And a lot of quantum mechanics is done by looking at specific Hermitian inner products on that complex vector space. So anyway, what we're seeing here is the sort of the first step in the direction of how you do quantum mechanics, and so there's a lot of applications down there. Again, we don't have time to do those applications. It's just a cultural note. Okay, all right. So what we're going to do now, we've got a brand new notion of dot product. We have this, revised, this Hermitian dot product, and we're going to come up with kind of analogous constructions that fit nicely with it. And it's just a kind of a sequence of ideas. Here we go. Our first one. This is the real dot product. I'm writing it as an inner product just for sort of notational purposes, but this is just plain old Math 212 dot product. That plain old Math 212 dot product has a nice dovetail with transposes. We didn't really talk about this at the time, but if you have this construction where there is a matrix factor on the left of a dot product, compute, and it turns out you can take that matrix factor on the left, you can put it over onto the right by transposing. Yeah. Anyway, it's a true fact. Nice little dovetail in the sense that the construction of the dot product and the construction of the transpose between the two of them share a nice property. Now this calculation is something you can all do. Notice the very first step that we have here is an algebraic observation we made last time, that a dot product is a transposed matrix product. Right? There's that we did this when we were talking about orthogonal matrices. Everything else is just kind of moving parentheses around. No big deal. Okay, well, if the dot product dovetails with transposes, here's a reasonable question. If I tweak the dot product, what is the corresponding tweak of transpose that allows me to preserve that connection, to make that same dovetail still fit? Right? In other words, what fits in with our brand new Hermitian dot product in the same way that transpose did with the regular dot product? And this is just a calculation. Here it is. It's called the Hermitian transpose. Very natural terminology to think about it. This is a construction that plays a role analogous to the role of the transpose when you're doing Hermitian stuff. So Hermitian transpose is a great choice of words. The formula is not terribly surprising. It's the conjugate of the transpose of the matrix. And when I say that it dovetails with the Hermitian dot product, what I mean is, just like in the real case, if you have a matrix factor on the left in a Hermitian dot product, that matrix factor on the left, you can put it over to the right if you Hermitian transpose the matrix. Okay. All right, now I'm going to leave this as an exercise for y'all to prove. First thing I'd like you to do is take a whack at this yourself. The way that you're going to do this is pretty much rip off the ideas that happened up here. The ideas of how we saw how the transpose fits with the dot product. Reinterpret the dot product as a transpose matrix product. Make an argument about how transposes work on products. Redo parentheses, etc. So follow that same template. Adapt appropriately to this admittedly a little bit different situation. Now this is no longer a regular dot product. Now this is a Hermitian dot product. There's different formulas for it. See the previous page. Right? Adapt that argument above, and that will allow you to go from here to here. Very reasonable exercise. If you get stuck on this, there is an old midterm exam question some years back. I don't remember exactly how far, where this was the question, and so the answer is in the solutions. So please give it a try on your own first. But if you get stuck, that's where you can find the answer. Quick comments about terminology. This terminology of Hermitian transpose I think is fantastic. It is also sometimes called conjugate transpose. I think this makes great sense too. Look at what the construction is. Right? This construction that we're doing is literally the conjugate of the transpose of the matrix. Right? So conjugate transpose. Very natural terminology. Okay. Okay, there's another term, adjoint. So this is an alternative term. This is in very common use. And y'all should be aware, heads up, if you hear the term adjoint, that's what this means. Now you may be having flashbacks to section 1.7. Do y'all remember this thing that the book called the adjoint back in section 1.7? And I think I made a comment in class at the time that, it's the same word that applies to a different thing in a later context. Here we are. This term adjoint much more commonly these days refers to this. And thus, as I commented back in chapter 1, that thing, that weird construction from chapter 1, more commonly called the adjugate. Okay, anyway, terminology. Okay. All right, we had a new notion of dot product that now gives us a new notion of transpose based on how those tools previously related to each other. Okay, now we keep going. The old notion of transpose connects to our old notion of symmetry. After all, a symmetric matrix is a matrix that is its own transpose. Right? So, analogously to what we did before, if we have a new notion of transpose, kind of a Hermitian notion of transpose, a notion of transpose that makes sense in our new context, shouldn't that give us a new notion of symmetry? And absolutely, it does. We say that a matrix is what I would like to call Hermitian symmetric. I think Hermitian symmetric is the sort of the way to think about this notion. If it is its own Hermitian transpose, totally analogous. In the real context, a symmetric matrix is one that is its own regular transpose. Okay. All right. Apologies, but the more common term for what I would like to call Hermitian symmetric, the more common terminology is just Hermitian. So heads up, that's the word that gets used. I have to kind of remind myself, every time I hear the word Hermitian matrix, I have to think to myself, okay, what they meant was Hermitian symmetric, and so in my mind, I'm going to think of this as something that behaves kind of like a symmetric matrix, and yet in a Hermitian context. Right? So I encourage you to think along those same lines. Okay, so a couple of quick observations. Remember, if you have real dot products, a matrix factor on the left goes over to a matrix factor on the right, but you gotta transpose it. Well, wait a minute. If it's symmetric, then it is its own transpose, and therefore you don't have to do anything. Analogously, if you have a Hermitian dot product with a matrix factor, that you want to move over? Well, you have to Hermitian transpose it, but if it is Hermitian symmetric to begin with, Hermitian transposing doesn't do anything there, namely you don't have to do anything. Okay, so this is going to end up being the powerful feature, one of the big powerful feature of Hermitian matrices. You can just move them from one side of a Hermitian dot product to the other, and nothing happens. It's very weird. Okay. All right. I'm going to show you all a couple of quick proofs. These are actually quite quick. We've developed some odd tools to work with. This is, by the way, I like to think of, where we are right now as being kind of an Alice in Wonderland kind of a situation, in the sense that, we're seeing a lot of familiar concepts, but they've all been kind of messed up a little bit, right? I mean, we have a dot product, kind of. It's weird, but it's kind of like the dot product, but they're calling it a dot product. Okay, strange. We have a Hermitian sort of modified notion of transpose. We have a new notion of symmetry. Everything's familiar, but everything's weird. Just like in Alice in Wonderland. Turns out that with this setup, we are now surprisingly poised to prove some very powerful theorems. And here we go. We're going to start off with looking at real symmetric matrices. The first observation is that real symmetric matrices are Hermitian. This is an easy one. Remember what Hermitian means. Hermitian means that it is its own conjugate transpose. Well, what happens when you take a conjugate transpose of a real symmetric matrix? Well, it's real. So when you conjugate it, nothing happens. Then when you transpose it, well, this is a symmetric matrix. When you transpose it, nothing happens. So, immediate observation, real symmetric matrices are Hermitian. And this leads us into some crazy results. Here we go. First result, if you have a real symmetric matrix. Surprisingly common situation, by the way. The eigenvalues are all real, and loosely speaking, the eigenvectors are all real, and I'll modify the language on that. I'll talk about that in a few minutes. But roughly, just for sort of ease of communication purposes, the eigenvalues and eigenvectors are all real. Now, this does not seem likely. Let me just remind you, we've computed a bunch of eigenvalues and eigenvectors. On multiple occasions, the eigenvalues have been complex. When we were talking about eigenvectors previously, we never made any mention of the relevance in any way of symmetry. What does symmetry have to do with anything? Right? This seems kind of implausible. Now let's think about how might we prove this result. Let's take a section 5.4 point of view on how we might prove this. Well, we've got formulas for eigenvalues. They're roots of the characteristic polynomial. I guess I could, for a symmetric matrix, maybe the characteristic polynomial will kind of simplify in some way because of the symmetry. But if I write out this great big characteristic polynomial, how would I go about proving that the eigenvalues are all real? That's really weird, right? Maybe you could think in terms of, okay, up to 3 by 3, I could actually write down the polynomials. They're just cubics. Those aren't that bad to factor. Maybe you feel like you could do that, up to 3 by 3, sort of, brute force. Notice, no such constraints here. This is for any dimension. You could have a 12 by 12. This is true, and we couldn't begin to think about writing out the entire characteristic polynomial for symmetric 12 by 12 matrices. Yikes. Okay, so this is a shocker. It's a really short proof. Here we go. Suppose you have an eigenvalue and an eigenvector. Right, now, we don't know anything about these eigenvalues and eigenvectors yet. My goal is to show you that they're real. Right, but I certainly don't know that yet. So I'm going to, with making no assumptions, I'm going to look at this construction here, Hermitian dot product. Now, let me share a thought. The first time I saw this, I remember thinking to myself, Well, yeah, but you just made the Hermitian dot product up. Right? You pulled this out of thin air. Can you just start doing stuff? Isn't the fact that your construction is manufactured and arbitrary, doesn't that mean that anything you do with it is arbitrary? Not right. Not quite. It may be arbitrary, but we have seen properties that it has. You can prove the properties of the Hermitian dot product. That's not arbitrary. Right? If you write down a random formula, it's not going to have nice algebraic properties. You can't do algebra. You're dead in the water if you make up some meaningless operation, right? We wrote down an operation here that has really nice and natural algebraic properties. We are not dead in the water. We can do algebra. And that's what's going to allow us to draw some nice conclusions here. So here we go. First thing, this matrix, by assumption, matrix is real and symmetric, and therefore Hermitian, and therefore I can take that factor of A and whip it over to the other side. Right? First step. Real symmetric matrices are Hermitian. We've already shown that that is what Hermitian matrices do. Okay. Next. V is an eigenvector. Eigenvalue lambda. Let's write that down twice. There you go. Well, let me zoom back in here. AV is lambda V. Now, I still don't know if I haven't shown that these are real numbers and real vectors yet, but I do know that that's true. Okay. Now, scalars factor out, right? So I can take that lambda, factor it out. I can take this lambda and factor it out. Slow down. You can factor out scalars, but when you factor out scalars from the right factor, don't forget to conjugate because of the conjugate in our definition. You have to do that, otherwise your properties don't make sense, right? So that conjugate is, that's not arbitrary, that's what makes the construction meaningful and natural. So not forgetting to conjugate the factor on the right, I get here lambda bar, not lambda. And, lambda bar. Then don't forget with a non-zero, eigenvectors are non-zero, right? Very importantly, we saw that non-zero vectors self-dot products are never zero. Therefore, I can cancel this non-zero common factor, and we win, right? Lambda is equal to lambda bar. This number, whatever it is its own conjugate, and therefore that eigenvalue is real. Just it falls into our lap. Amazing that this works. It works because we can do algebra. We can do algebra because the construction that we defined that seemed kind of manufactured and made up and silly has nice algebraic properties. We made it to have those nice algebraic properties. So this is ultimately, it's natural, not arbitrary. Okay. All right. Now, I'll also point out while we're here how important it is that non-zero vectors are never, do not ever self-dot product to give zero. Right? That's what allows you to cancel. You can't cancel a common factor of zero. You can only cancel a common factor if you know for sure that it's never zero. And that property here, never zero, right, is what makes that possible. And that's why, by the way, if you tried to go through and do something kind of along these same lines, but if you tried to do it with the regular old, plain old Math 212 dot product, crash and burn. Because you don't have that property. You have non-zero vectors whose self-dot product is zero. And then you can't do the proof. Everything fails. Okay. All right. Okay. Yeah, so here's what we've got then. Real symmetric matrices. We just showed the eigenvalues are real. Now, loosely speaking, I'm going to say the eigenvectors are real. This is really an easy argument. If you have a real matrix and a real eigenvalue, what is A minus lambda I? A minus lambda I is also real. Lambda was real, A was real, everything in sight is real. We're then doing a null space to find eigenvectors. Null space of a real matrix, that's going to row reduce to a real reduced for echelon form. Solve for your pivot variable, play the game, and do the usual null space thing, and there's just no opportunity for complex numbers to come up. So what you get is a basis for your eigenspace consisting entirely of real eigenvectors. Now, so that's not quite the same as saying all the eigenvectors are real, but you can choose a basis for the eigenspace that is all real. It does remain that if you, for whatever reason, would like to, if you want, then you can take one of these real eigenvectors and you can multiply it by a complex scalar. And now you have a complex eigenvector, so that's also fine. But the point is you don't have to. You can find all real eigenvectors. Okay. All right. Shockingly powerful result. I mean, again, can you imagine how brutal this would be in a sort of a chapter 5 context? Hermitian dot products make it easy. Okay. Related fact. Real symmetric matrix. Suppose you have a couple of distinct eigenvalues, let's just say. Corresponding eigenvectors. To a great surprise, these eigenvectors with distinct eigenvalues are orthogonal. Super weird. Now, again, I say this is weird because, look, we've seen so many instances where this didn't happen, or, this punchline didn't happen. We've computed loads of eigenvectors. And go back and look at it. Look at the matrices that we wrote down. Look at the resulting eigenvectors corresponding to different eigenvalues. And see if they're orthogonal. And they're mostly not. Right? So again, really? They're going to be orthogonal every time just because the matrix is real and symmetric? It's really a surprising result. Again, think in terms of how would you prove this from a chapter 5 standpoint. It's unthinkable. Right? The difficulty of writing all that down, I mean, it's completely intractable. But it's easy with Hermitian dot products. Again, it's just sort of a clever observation. Take these two vectors, v1 and v2, write down this construction arbitrarily. We've got a Hermitian matrix, and therefore A will whip over to the other side for free, just like we did in the last proof. V1 is an eigenvector. V2 is an eigenvector. So rewrite those as lambda 1, v1, lambda 2, v2, respectively. Factor out the scalars. Lambda 1 factors out. No problem. Lambda 2 factors out. Now, you might be thinking, wait a minute, don't you have to conjugate that, right? This is a factor on the right. You're supposed to conjugate when you factor out on the right. But we already know that the eigenvalues are real. Since from the previous theorem, we know that this eigenvalue is real. I guess you could conjugate it if you want, but it doesn't matter. Okay. All right. Now, subtract everything to the other side. Group. It groups up like this. We know that this is not 0 because by assumption these are distinct eigenvalues. Because they are distinct eigenvalues, this is a non-zero factor that I can cancel off. And the nice punchline is, as desired, V1 and V2 are orthogonal. That just works. Very unexpected, but hard to argue with. Okay. All right. Okay, really powerful results. Okay, now there's some other neat things that you can say about these kinds of cases. The first thing I have to do is talk about language a little bit. There's some really intimidating sounding language that I want to demystify a little bit. So don't forget we had this notion of two matrices being similar. Similar means conjugation. All right. Okay. So here's the refinement that I want to make of this idea. Let's think about, two matrices are similar if there is some conjugation, but then keep in mind, there is the further detail of what is that matrix? P. And if not only does P exist, to allow for this conjugation, but if P has a further property, if P has some descriptive adjective, whatever it might be, if P has some other characteristic, then not only is there a conjugation, but there is a conjugation by a special matrix. So any feature of P becomes a feature of the similarity. So the idea, for example, here is let's look at a couple of matrices that are similar, like so. A and B are similar; they're conjugates of each other. Suppose you further know that P, not just some random matrix off the street, right? But if P is known to be an orthogonal matrix, then okay, A and B are similar, yeah. But they're not just similar. They are similar by way of a special matrix. They're similar by way of an orthogonal matrix. So the similarity itself, there is something sort of orthogonal about the similarity. The conjugation is by an orthogonal matrix. So we say orthogonally similar. So anyway, the concept I want you to notice, the little pattern I want you to notice, is that similarity means conjugation, and as a result, any feature of the conjugating matrix becomes an adverb modifying the nature of the similarity. So orthogonal P means that the matrices are orthogonally similar. Okay, along those same lines, what does it mean for a matrix to be diagonalizable? Well, diagonalizable means conjugate to a diagonal matrix. So there's another conjugation. It's another similarity to a diagonal matrix. Okay, fine. So, analogously, if you know more information about the conjugating matrix P, then you have a refinement of the notion of diagonalizability. So diagonalizable still means that P exists. The fact that P is orthogonal, the fact that the conjugation is special by way of an orthogonal matrix, means that we're talking about an orthogonal diagonalizability. Or we say that the matrix is orthogonally diagonalizable. All right, so that's all it is just the idea that, we're taking one idea and we're refining it with an adverb. Not that big of a deal. But the resulting terminology, I think, is quite intimidating. If, I don't know, just that term, orthogonally diagonalizable, it's kind of scary. That's all it means. Is everybody on board? All right. So why am I telling you all this business about terminology? It's because this is a last property that we're going to see of real symmetric matrices. We already know that real symmetric matrices have all real eigenvalues. We already know that the eigenvectors are orthogonal. What we don't know yet is, but how many eigenvectors are there? Right? Are there many missing eigenvectors, or do we get that fingers crossed maximum possible number of eigenvectors? So what this theorem is saying is yes, you get the maximum possible number of eigenvectors. A real symmetric matrix is diagonalizable. And, well, if it's diagonalizable, and we already know the eigenvectors are orthogonal, then that means that the real symmetric matrix is orthogonally diagonalizable. Okay. So really, all this discussion about terminology up there is just so I can say this theorem in a nice, pithy kind of way, crisp and succinct. Real symmetric matrices are orthogonally diagonalizable. All right, how are we doing? Is everybody on board? Okay, this makes for a pretty good stopping point. We got a little bit more I want to say about this on Friday. We'll do that then. Y'all have a nice day. See you later.